Okay. Good morning, people. I know waiting is painful. So some of you who have already logged in and are sitting, I can view their video. And what I see is there are quite a number of students who still need to log in, or they are still to settle down in their classroom. So we'll give them a minute, maybe a minute or so, and then we'll start with our class. Okay. Right click, allow download. Good thing. Okay, so let's begin. Okay, let us begin. Today is our last lecture, last class, by the way. Okay, we would summarize our shear strength. We started with shear strength the other day, and today I intend to continue. But of course, like I said, the chapter on shear strength is a huge chapter. At IIT Bombay, what we normally spend about maybe about 6 or 8 hours on this particular chapter, doing some problems as well. So today I intend to in fact spend the second hour and briefly continue with where we left the other day. If you recall, the other day we started with a concept, a simple concept of how a stress at a point can be written as. If a soil mass is loaded by a number of force or traction, surface traction, the stress which is induced on any plane inclined at alpha within a small point, or we in fact zoomed in into the point into an element, and we said the element can be a rectangle like this shape, or just to give a regular shape to simplify the two normal planes. So the vertical plane is usually represented as the major principal stress, because the larger magnitude of stress is assumed to be applied in the vertical direction. So if we had to resolve this in terms of Mohr circle, sigma 1, which was greater than sigma 3 in this figure, we could plot sigma 1 as the greater stress value, sigma 3 as the minor stress value. So this was the minor stress, likewise this was the minor principal plane. So having this state of condition, we stated that this yellow dot over there is the pole, and we identified pole in such a way that you can draw planes from pole at any angle, and the position where or the spot where the planes intersect the circle would give you the XY coordinate, or the normal stress, shear stress value on that plane. Okay, and that normal stress, shear stress were also shown by this set of equations. We went on to explain a concept of how failure and yield is identified in soil mechanics. We took an example of mild steel wherein you had a yield point and a failure point. Remember, all these are stress strain curves. A non-linear elastic where you had a loop followed by a perfectly plastic, and if I go down, we said it is only the last two figures which are of interest to us. In fact, in most of the soil mechanics which we teach in third year, it is only the second last figure which is of interest to us. If you want to go into research, it is the last figure wherein you have a work hardening or a work softening material. Okay, it is only the elastic, perfectly plastic material which is of interest to us. An example of elastic, perfectly plastic is Mohr-Coulomb. We'll start with Mohr-Coulomb today. Mohr-Coulomb, in fact, we look at Mohr first. Okay, what Mohr in early 1900s stated was materials will fail when you reach a shear stress value. If you look at this example of this figure, which is a plot of shear stress versus normal stress. So what Mohr said was, if you reach a particular shear stress value which is a unique function of the normal stress, In other words, you are on this curve. This curve identifies shear stress, which is tau at failure, which is a function of normal stress. So, in other words, Mohr identified failure as a curve which is a unique function of normal stress. Okay, so if we want to look at the same thing in terms of the element, this is the same element. This time it's drawn in a squarish manner, where normal stress is sigma 1 and horizontal stress is sigma 3. So normal vertical stress undoubtedly in this scenario is shown to be greater than sigma 3. Okay, so if we have a function, if we have a relation between sigma 1 and sigma 3 on any plane, for example this plane which is shown by broken line, you will have normal stress sigma and shear stress tau developed. But what if you reach a situation such that this normal stress sigma 1 and sigma 3 have a unique relationship such that this tau value reaches failure. So you have a tau value which reaches failure. Likewise, the normal stress is also on the failure, meaning the failure plane. So I have identified this broken line as the failure plane. Okay, let me look at this figure carefully again, and just to look at this figure again, as the same figure which has been zapped from the previous slide. What we have said is this tau f and sigma f would be a unique function on this unique plane, okay, which is at failure. In other words, if I'm confused about this figure, but if I'm recall what is my Mohr circle and plot this in terms of Mohr circle, I have the vertical axis as tau, horizontal axis as sigma. And remember, sigma 1 is greater than sigma 3, so that's the Mohr circle for me, although I have plotted a semicircle. Okay, so what I have zapped this broken line, I have carried this broken line parallelly and replotted such that it originates from this pole. Remember, this point is the pole which coincides with sigma 3 only if for this condition. Okay, so I have drawn this line. What we say is this coordinate of tau value is at failure. So I have given tau failure. Similarly, sigma value is at fail. This is at normal stress on the failure plane. So I have given sigma f. Right? Let me move on. The important thing between what we have is Mohr failure envelope is the Mohr failure envelope is a curved envelope. It's not a straight line. It's a curved envelope. We will look at the straight line scenario in the next slide. But what it means is you can have different combinations of sigma 1 and sigma 3. Likewise, this is the first Mohr circle with a combination of sigma 1, sigma 3 such that on that plane you have reached failure. Okay, so if I go and have another combination of sigma 1 and sigma 3, I have the same plane, remember the same failure plane at the same angle, and this time this combination gives me another Mohr circle which is at failure. Likewise, I can have various Mohr circles to envelop all the Mohr circles such that the envelope only touches at one single point. This envelope, like we just said, is a curved envelope, right? And it's likely called as Mohr failure envelope. So somewhere down the road, if we have this a Mohr circle which is lower than the envelope, so it's smaller than the envelope, we normally call this state as an elastic state. That's what is assumed. If you have not reached the failure envelope, just to remind you from one of the figures which we looked at last, if I go back, it's this figure. Remember, in this figure we said it's elastic up to the yield point, and unfortunately in this figure the yield point and the failure point are the same. So it is elastic up to yield or failure, and thereafter it becomes perfectly plastic. So if I go to the current slide, yes. So this circle being lower than the yield or the failure envelope, this is elastic. this states this is an elastic state. Likewise, the circle B, which is higher than the Mohr circle, we say it cannot exist. Such a stress state will not exist such that you exceed the envelope. Okay. So somewhere, let's look at Coulomb. Remember, Coulomb came much earlier than the Mohr. So Coulomb, yes, I think 1776, and the other one is 1900s. So it's much earlier. So Coulomb, in fact, made a statement which is something we are very familiar with. So he says there is a stress dependent component. So in shear strength there is a stress dependent component, and likewise there is a stress independent component. Okay, the stress dependent component is what we are familiar with. If I have a block and I slide this on the surface, if I slide this, the amount of the stress I require to slide, meaning the shear stress. Remember, sliding is shear stress. So amount of stress I require to slide this is dependent on the weight of this block. In other words, if I apply additional load on the block, it will require a greater stress or a greater force to slide. This is something which we all have studied in elementary physics. Okay, so the force which I apply, or the shear stress which is required, it depends on the stress. So this is the stress dependent component. The other thing which is a stress independent component, what Coulomb said is cohesion. Okay, it is cohesion. And many decades later, in fact it's only in the last 50 odd years, we have started to write this as intrinsic cohesion rather than cohesion. Intrinsic, or some textbooks it's written as apparent cohesion. This apparent or intrinsic means it is not the true cohesion. Okay, true cohesion of soil, if you speak to some of the research students today, they say true cohesion of soil is 0. Unfortunately, Coulomb did not realize in that period that true cohesion of soil can be 0. But nonetheless, we faithfully, even in majority of the textbooks even today, we faithfully follow the Coulomb's concept of cohesion. So if I want to plot this, the findings of Coulomb in our tau versus sigma plot, which we are familiar with, what Coulomb said was there is a stress independent component. So that is the value where there is stress is 0. So I have a constant value of C, which is my cohesion, and the envelope is inclined at an angle which is phi. So this, in other words, this inclination is the stress dependent because it varies with the stress value. So if I have this equation of this curve, I have tau, which is the shear stress, equals to C, which is the stress independent, plus sigma tan phi. Okay, and somewhere down the road, again because engineers were smart, they said because the shear strength of soil depends on the effective stress, so they put everything in effective. So tau equals to C prime plus sigma prime tan phi prime. That's the dash or the prime over there. Okay, it is not shown on this equation, but nonetheless what it tries to show is that the shear strength of soil depends on the effective stress, not the total stress. Okay, so, but I write this as tau, not tau prime. I hope you understand that the water will not be able to carry any shear stress. That is why tau and tau prime are the same. Okay, let's move on. There are few important things which you need to look at when we study Mohr-Coulomb. Why we say Mohr-Coulomb? Remember, Coulomb came out in a different era. Mohr came out with a different era. Again, sometime in early, this 1900s, some bright engineers, they decided to combine the two. So they came out with Mohr-Coulomb failure theory or criteria. So Mohr-Coulomb failure initially we had a Mohr hypothesis. Coulomb came out with this a set of equations and someone combined the Mohr circle with the envelope, and the envelope this time was a straight line. Okay. So if I have to plot this envelope within the this combined with Mohr circle, I get something like this. That is my tau, this is my sigma, and that is my Mohr circle, and that is my Mohr-Coulomb failure envelope, which is inclined at phi. I can rewrite this thing, the failure envelope, which is my alpha. Remember, this is the failure envelope which starts from the pole over here and it's inclined at alpha. This alpha, the failure envelope, the slope of the failure envelope can be expressed in terms of this phi or phi prime if you are more happy with primes at this level. We will introduce prime, of course, at later part when if you study shear strength in greater detail, you will then venture into prime. But today, let me just write this as phi. So this alpha can be expressed in terms of phi by this slot. If you look at this Mohr circle over here, I have this alpha that starting from origin, this broken line intercepts the same point. So this value, if this is alpha, elementary trigonometry tells me this angle should be 2 alpha. Okay, so I have 2 alpha over here. Okay, and inside would be 180 minus 2 alpha. If this angle is 180 minus 2 alpha, this is phi, and I know this is 90 degree. I can write this as 2 alpha equals to 90 plus phi, okay, or alpha equals to 45 plus pi by 2. This gives me the slope of my failure plane. There are other two important concepts, and the second one which I am looking at right now is that the shear stress on the failure plane. Remember, this is my Mohr circle, that's my failure plane, okay, and this point is that is my failure envelope, and this is my failure plane. Apologize for mixing up the words. This is my failure plane, and it hits this point circle at this point over here. What we see is, if I have drawn this circle, this point is not the topmost point of the circle. If I have to zoom in, the topmost point of the circle is slightly higher. So this is what we try to say, that let me zoom out please. The shear stress on the failure plane, that's this plane, is not the maximum shear stress in the element. So the maximum shear stress in the element would be, if you look at this carefully, would be at 45 degree plane. In other words, if this same element, if I induce stresses such that the failure occurs on the 45 degree plane, not on the alpha plane, in this case, only in this case, my maximum shear stress would coincide with the shear stress on the failure plane. So when it coincides with the failure plane, in this case, this point should be passed through the topmost point. It can only pass through the topmost point if this envelope is horizontal. Okay. Now this horizontal envelope or the 45 degree plane is, you can do test under this scenario, meaning the test conditions will dictate how this envelope can be formed, and like I said, it will be a part of your further shear strength study. In today's class, we will just visualize this first figure, that the shear strength on the failure plane is less than the maximum shear strength or shear stress which is induced in the element. Okay. Let me go to the next slide please. The next one is the same Mohr-Coulomb failure, the expression of C and phi, the parameters can be expressed in terms of sigma 1 and sigma 3. Okay. Let us look at this figure over here. That's the Mohr circle. So I have the failure envelope inclined at phi. If I extend this failure envelope backwards, it intercepts the horizontal axis in the negative direction. But I'm not interested in negative because we are not doing anything. What I'm interested in is what is the horizontal component. If this is phi, because the slope is phi, and this is my c, this horizontal component, elementary trigonometry tells me is c cot phi, this length. Okay, let me go back to this circle again. I have this a radius which is normal to this envelope, and if I look at this triangle, the big triangle which is formed, this triangle, this is perpendicular, the other thing is hypotenuse. So if I want to write this as sine phi, which is perpendicular upon hypotenuse, I get perpendicular is the radius, which is sigma 1 minus sigma 3, okay, and hypotenuse is this whole lot. Okay, I can write this in form of this equation over here. Let me zoom in. So sine phi equals to perpendicular, which is the radius, over the hypotenuse, which is over here. Okay, now I can play around with these terms, meaning take this on the left hand side, collect sigma 1 on one side. That is what has been done over here, but the final equation is something which is of interest to me, which is sigma 1 equals to sigma 3 times 1 plus sine phi prime over 1 minus sine phi prime plus 2c cos phi over 1 minus sine phi of phi prime. Now please be careful on this. This equation is only valid if the Mohr circle touches the envelope, the failure envelope. Okay, this expression will only then be valid. Obviously, because this has a phi. So sigma 1, sigma 3 is again a function of phi. In some textbooks, rather than this equation, they have further simplified this using trigonometry, and I'll just go to the last expression over here. So if you use trigonometry, you have another form of expression. Rather than 1 plus sine phi over 1 minus sine phi, they have tan square 45 plus phi by 2, and rather than the second component, they have tan 45 plus phi by 2. That is something which is again the same equation, but this time in another form. Okay, let me the next slide please. In this the same equation which we have written at the back, okay, if you can carefully look at this, if what happens in a situation when c or c prime is 0, when this is 0, my my expression becomes sigma 1 equals to sigma 3 times this whole thing, or sigma 1 by sigma 3 equals to this a value. In some textbooks, this whole thing is written as obliquity relationship. If you will feel like remembering this term, what it means is it is the maximum, it gives you the maximum failure, or I must say the maximum slope of the failure envelope when c equals to 0. Obviously, this envelope would be at its own maximum inclination because c is 0. It gives a maximum inclination. You can go back home and try to plot this. If you try to plot this, you will see that when c becomes 0, the envelope, it gives a maximum inclination. In all the while we have more circles, we have only dealt with sigma 1 and sigma 3. Sigma 2 is usually ignored. It is because it lies in between sigma 1 and sigma 3, and in most of the conditions this can be ignored because it is not shown to affect the failure condition. Remember, failure condition is dictated by sigma 1 and sigma 3. If this is my Mohr failure envelope, or in terms of Mohr-Coulomb, if I make it into a straight line, this sigma 2 value does not dictate the failure condition. Over here I have an example of a test through which we measure the shear strength of soil. and we only have time to look at the direct shear test, which is the simplest of all tests. And let me spend the next 5 minutes just to explain this test procedure. If you have any question, please by all means stop me. I would be more than happy to explain something in detail rather than push the syllabus enough forward. In direct shear test, what we have is we have two halves. That's a shear box. We call this a shear box, and it is in two halves. Usually we clamp the two halves together, so the two halves, this shows that the two halves are moved slightly, but we clamp the two halves together and then fill this with soil. And once we fill this with soil, you put a porous stone at the top, bottom. You may put a grooved plate in between just to provide additional gripping at the two ends. But the purpose of this test is to slide the two halves away from each other. If I look at this carefully, before the two halves slide, it is important to see that if I apply a vertical stress from the top or vertical pressure from the top, it induces a vertical stress in the sample. Okay, so vertical pressure or the stress from the top, let's call it as sigma 1. If I apply sigma 1 and before the start of the test the two halves are together, they don't slide. I don't push the two halves relative to each other. If there is no sliding between the two halves, can I say there is no shear stress on this horizontal plane? Okay, I've applied a vertical load and on this horizontal plane there is no sliding. Remember, this sliding occurs in this horizontal plane. So if there is no sliding, can I say this horizontal plane is my principal plane? And because this is a larger magnitude, this is the major principal plane. Likewise, there should be a plane perpendicular to this, which should be my minor principal plane. So perpendicular to this, let's take this as this over here. It is this direction. And because in the start of the test, the two halves do not slide, they are just there. So that should be my minor principal plane. There is no friction, no sliding. Okay, no sliding along this in this direction. So a normal stress which is in this direction is my minor principal plane. Likewise, I can have another plane in the third direction which is again perpendicular, and this would be again my intermediate principal stress. So minor and intermediate, if you look at this carefully, before the start of the test, they have the same value or the same magnitude, right? This magnitude, if you can guess what is the magnitude of this particular stress value, it's not difficult to visualize that since this box is rigid, it is stationary, so the soil is not allowed to move horizontally. There is no bulging. If there is no bulging, theory of earth pressures tell me that this is static case, earth pressure at rest. Okay, we have not covered earth pressures, but for the time being visualize, or I would request someone to cover at your center that these stresses which are horizontally, they do not allow the soil to bulge. We call this as the K0 condition. So the stress which is on the vertical plane would be, if you are familiar with this, would be K0 times the vertical stress. So horizontal stress is K0 times vertical stress. Okay, we will look at an example wherein we look at this K0 in greater detail. Okay, this finishes off the case when the test has not started. What happens if you start to slide, if the two halves start to slide relative to each other? So in this, as shown in this cartoon over here, like I said, this has been zapped from British Standard BS 1377. You're most welcome to use the similar set of figure from the IS code. In this figure, what you see is the two halves have slid, they have moved relative to each other. If they have moved relative to each other, there is shear stress which is generated in the horizontal plane, correct? Because you are moving relative to each other. Over here lies a very tricky question. We said to begin with there are no shear stress on this horizontal plane, because of which this horizontal plane was the principal principal plane. Now if shear stresses are generated, it is no longer a principal plane, meaning the vertical stress which I have applied is no longer the principal stress value. Okay, if I want to generalize this statement, I can say in direct shear before the start of the test, the horizontal plane is the principal plane, but during the test and when I reach failure, meaning failure would be reached when the two halves slide and you reach a peak stress value. No, so up to failure, this plane, horizontal plane, is no longer the principal. In other words, the principal plane, they change their orientation during the test. This is a major drawback of this particular setup or test. There are of course other drawbacks, and let me move to the next slide to explain the other drawbacks. I would like you to go back home and look at this figure in detail. This whole shear box is kept in a water bath. I would like you to go back home and please spend some time to go through the reference either through this British standard or through our IS code. Okay, let me move on to the next slide to speak about some of the disadvantage. The very first one is drainage conditions cannot be controlled. Obviously the shear box, because it is sliding, I cannot control the pore pressure, meaning pore pressure which is developed, I cannot say okay, now pressure it's your turn to dissipate or it is your turn to stay there. This cannot be controlled. It is important to understand that even if you are testing clay soil, it is difficult to control the drainage no matter what you do. The second thing is failure plane is always horizontal. Remember, I have two halves which have started to slide, and during the sliding portion always the failure plane remains horizontal. This is again a major drawback, because in a soil element, when I have vertical and horizontal stresses, it is possible that the combination of vertical and horizontal stress, the failure plane is at angle alpha, and definitely alpha is not 0. The third one, stress concentrations occur at the boundary. Remember, I have a rigid container in which I have kept soil, and the stiffness of this rigid container is at least a couple of orders more than the soil. In other words, if I have a stiff material against a softer material and if I load it, stiff material tends to take more stress value. This is called a stress concentration. So there are stress concentrations along, especially at the boundary. The fourth one, the area of the specimen changes during the test. It is important to see that the area becomes smaller, because to start with, if I have a 6 centimeter by 6 centimeter sample, I start to slide, the common area between the two gets reduced. You can visualize this if you use your hands and then start to see which is the common window. Of course, IS code has said for each deformation value, you change the area. Whereas some of the international codes, they say no, you take the area as the same as starting area. This is of course a point of argument. If you're a research student, I would be more than happy to discuss this with you. The last one, the directions of principal planes. Remember, the principal planes were horizontal and vertical to begin with, but during the test they are not known. However, after the test we can evaluate the direction of principal planes, and I have just an example. After this we will spend about 10 minutes on that example to understand the direction of the principal planes in a direct shear test. I have listed down two questions in the problem sheet, but Like I said, shear strength is a big chapter on its own. It's huge, and in our 2 hours duration, it is practically impossible. If you visualize this over here, we have a whole semester over here for master student who study just a chapter on shear strength in detail. And they look at stress path, look at Mohr-Coulomb, they look at Cam Clay, they look at numerous under advanced soil model just to study the chapter on shear strength. However, for most undergraduate study on shear strength is at least 8 hours, if not 10 hours. But I would request that you go back home or in your regular classroom, you do justice to this chapter and not simply rely on 1 or 2 hours of brief introduction which we have done. Okay. Now I will continue with the problem sheet. We have probably done 2 questions. The third question is over here, and I would not spend time on this. It's fairly straightforward. It's the simplest of all questions. Let me see if I can. Oops. Where is my pen? Oh, what did I do? Okay. Is it something I pressed? Should I try again? The internet is still on, you see. Maybe, it has been low for a longer period and we just noticed. They can listen to me? Okay, please stay with us. There is some network issue over here. They're just trying to resolve. Give them a minute or so. Please stay with us. Done. Okay. Allow download. Okay. 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 Pointer. I need. Yeah, this is what I did. Yeah. Okay. Sorry for the hiccup. You know, we are back in business. Please, you know, thank you for bearing with us. We were on to this question number 3. I hope you have in fact got a chance to download today's file. Okay, because we had to do it again. Question number 3 is a very straightforward question. It says determine the shear strength, meaning it asks you to determine the tau value. We know that tau equals to, you know, C plus sigma tangent of, trying to write this as best as I can, tangent of phi. But you know, some of the bright engineers have told us this is not right. It should be C prime plus sigma prime tan phi prime, because the strength of the soil depends on the effective stress. So in this equation, if I plug my C prime value, which is 20 kilopascal, sigma prime, which is effective stress, total stress is 200, pore water pressure is 80, so 200 minus 80 is this value over here, and likewise phi prime is given, it should be somewhere here, that's 30. I plug in my numbers, I get solution to question 3. This was the most easiest of all the questions, and let me tell you, in your exam you will never get such a question. Okay, you may get a question which is somewhat related to the next one, and I'm going to quickly jump to the next slide to show you the next question. Now, because of the lack of time, I would not allow you, or I must say advise that you go through this question. What I would simply explain the question is, it shows the question shows the results of a direct shear test. Okay, and some values have been given. So it says the sample has failed when the shear stress was 41 kilopascal and normal stress was 65. So tau and sigma values have been given, okay, on the failure plane. Okay, shear stress and normal stress were so and so. So these values have been given. It says assume intrinsic cohesion to be 0, that is C prime to be 0. Draw the Mohr circle. Remember, it's a loose sand, direct shear test, no pore pressures are generated, it's drain test, so all my stresses would be in terms of effective stress. Okay, then it moves on to determine various other things. We will look at this as we go through the solution. We have about 10 minutes, and I can finish off this solution within 5 minutes if you know, if you're with me. Let's look at the first part, just the first part, and I'm going to go to the next slide, which shows the solution to the first part. In the usual direct shear test, we have a plot of tau versus sigma. Okay, this is our usual plot, and the values have been given as 41 is the shear stress value, it means it is the y coordinate, and 65 is the normal stress, so it's the x coordinate. And these are the measurements which were taken on the failure plane. Remember, in direct shear test the failure plane is horizontal. So if these are the values on the failure plane, in other words, these values should be on my failure envelope as well. Okay, so with this coordinate, and given that the cohesion or the intrinsic cohesion is 0, I can join the 0 value to this coordinate to draw the failure envelope. So this broken line over here is the on which this is my normal stress and shear stress value when the sample has failed. I am aware that if I have a Mohr circle which passes through this point, this line should be tangent to the Mohr circle. Remember, it should only intersect the Mohr circle at one point. In other words, using this coordinate, if I draw a Mohr circle, okay, sorry, never mind. If I draw a Mohr circle, okay, apologize for this small, color over here. Clear? Okay, thank you. So if I draw a Mohr circle over here, this point should be on the Mohr circle as well as this line should be tangent. For this to be tangent, I draw a normal to this, meaning I draw a perpendicular. This perpendicular should show that I have a Mohr circle and this is the perpendicular, meaning it is the radius of the Mohr circle in a way that this becomes the tangent. Okay, it is again elementary geometry. So I can, using this radius, I can draw a Mohr circle using this radius. This is my Mohr circle at failure. Remember, it is the Mohr circle at failure and this is failure point. Okay, so the first part of the question was draw the Mohr circle. I have just drawn this. The question continues to say what is the friction angle, phi prime value. Okay, phi prime value. Phi prime value you just read out of the gradient of this slope, which is 32 degrees. Okay, the next part of the question says what is the Mohr, draw the Mohr circle for the initial case. Okay, initial case. Let me go back to the question. Can I go back to the question? Yes. Oops, it's taking a long time, sorry. That is the question. So it's the first part of the question was draw the Mohr circle, we have done this. It says angle of shear resistance, we have done this. Then it says draw the Mohr circle for the initial condition when only normal stress of 65 kPa was applied. Remember, normal stress is 65 and shear stress is 41 at failure. So before the start of the test, just normal stress was applied, shear stress was not 0. You are asked to draw the Mohr circle. There is a condition given, K0 value. Remember, we said horizontal stress is K0 times the vertical stress in case there is no deformation. And this K0 value is related to Jakey's K0. Now over here we are trying to introduce a term called Jakey's one-dimensional consolidation equation or one-dimensional compression equation, which is K0 equals to 1 minus sine phi prime. Now I would not be in a position to explain this in this class, but for the time being take it as a tablet that if there is no horizontal deformation, K0 is given by this value provided there is a rider. You deal with loose sand or normally consolidated clay. In this case this is loose sand, so use of this equation is valid. Okay, so it says draw the Mohr circle for the in situ case. Let me go to the current slide. So for in situ case, I know my sigma 1 value is 65, that's over here. My sigma 3 value is K0 times 65, so K0 is 1 minus sine phi prime is 32 degrees. This gives me the Mohr circle when the test was just started, meaning there was no horizontal load, only vertical load was applied. So when only vertical load applied, this value over here was my major principal stress value. This was my principal stress value. When the sample failed, the Mohr circle is this value. In other words, the plane on which shear stresses are 0, that's this value is my major principal stress when the sample is failed. and this is my minor principal stress when the sample has failed. Okay. I'll go to the next slide. The question says find the pole. You're also asked to find the pole. Remember, this is the failure point, and failure point occurs on the horizontal plane. Meaning, if I use this definition of pole, the plane which is horizontal, it intersects the point F. So if I go back, this point over here should be my pole P. Okay. So from pole, the question says draw the find out the orientation of the major principal plane and the minor principal plane. So major would be joining pole to this major principal stress value, and pole to minor principal stress value should give you the minor principal orientation of the minor principal plane. Okay. Question I think also asks, and this is probably the last slide, find the orientation of the plane on which the maximum shear stress acts. Maximum shear stress is the topmost point. If I join pole to the topmost point and find out the orientation, this would give me the orientation of the plane on which the maximum shear stress acts. Now we have quickly gone through this question, but I would request that you go back home and draw this on a graph paper and then follow the question carefully. If you follow these slides, keep the slides in front of you, this question is a piece of cake. But let me just caution you, it is one of the best questions in direct shear test. And I think I don't remember where I borrowed this question from, but this question I believe if you have followed this question carefully, the direct shear test will be very simple to understand. Okay. With this, I conclude today's session. It was fun teaching via this medium, although in some of the classes, I admit that we had to rush. We had a lot to do in 15 classes, and I'm not sure how much of this was very fruitful, how much of this you could digest. But it would be easier to digest if you go back home and really look at the slides before coming in for the next class. I conclude. If you have any questions, please ask. Otherwise, we would have to end this session in the next 2 or 3 minutes. What I see is many of the centers have the videos switched off.